15.6, tangent planes and linear approximations. So in the same way, you guys use derivatives to compute many applications. I mean, we don't have to list them all, but you guys already know. Well, one of the most immediate applications of finding the derivative is to find the equation of the tangent line at a given point. Okay, so but well, what is the 3D version of this situation? So rather than having a curve, we're going to have a function of two variables that describes a surface. And at the same, and in a similar way, we are going to find the tangent at a given point. But that tangent can't be just a line. It's going to be this time as well as a plane. All right? Because that's in a way the 3D version of a line. I mean, equation-wise, because the equation of a plane contains all variables raised to the first power, right? Well, so what else do we need? Remember how we define this, how do we call implicit functions? So, because in many cases, like the equation for the surface that describes what's that? An ellipsoid or a sphere. We can't solve for any of the variables, even if we, so, I mean, if we try to set our z as our dependent variable, okay, try to solve for z, you're going to get plus minus the radical, right? So we can't get z explicitly as one function of z, but rather we get two of them, right? We get two of them. So, but still we need to keep working on finding this implicit functions. Okay, let me get my notes first. So, where are you? Okay, right here. All right. So, if we're given this function f of x y z equals to 4x squared plus 4y squared plus 4z squared equals to 36, in this case, this is a function. This is an explicit function of f where that contains, in this case, three variables, three independent, one dependent. So they're asking us to describe the level surfaces given by f of x, y, z equals to 0. That means we're going to set 4x squared plus 4y squared plus 4z squared minus 36 equal to 0. Okay, and I think the equation already looks familiar, right? So let's get in a form that we can easily describe this. That is, okay, let me get the variable terms on the left hand side. That is 4x squared plus 4y squared plus 4z squared equals to 36. And well, all the variables are positive and raised to the second power. The coefficients are all the same. That makes me think of a sphere. So let me divide both sides by 4 to find the actual radius of that sphere. That is x squared plus y squared plus z squared equals to 9. All right, so the surface described by this function, isn't that a sphere of radius 3? So that's a sphere of radius centered at the origin 0, 0, 0, right? Good. Let's have a look at another example. For the function of three independent variables x, y, and z given by f equals to x plus 3y plus 9z equals 12. I think by looking at the powers of the variables, you already know what this is going to be, right? So that is x plus 3y plus 9z plus 12 equals to 0. Keep the variables on the left. X plus 3y plus 9z equals to negative 12. What does that describe?
Ellipsoid?
An ellipsoid. Well, that would have been if we had the variables squared, right? So all variables to the first power. A plane, right? A plane. And well, unlike the sphere for which we could describe its radius in the center, there's a bunch of things we could tell about this plane, like it has a direction vector 1, 3, 9. It has intercepts, whatever those three intercepts are, x, y, and z. But no need. Just all we need is to recall what these are. What else do we need before getting into the equation of the plane? Number one, let's recall how do we write an equation of a line containing a point and having a direction vector. Again, let's recall that lines in space do not have rise over run. They are described or represented by a direction vector. Still, they have an initial point, like the y-intercept for the line, right? Also, we need to recall how do we get the equation of a plane that contains a given point and a normal vector, which happens to be the same vector components for the line that actually goes across the plane, like stabbing the plane, forming a 90 degree. And well, we did the derivation to get this, the equation of a plane that is a vector dotted with some points, the difference between with some points, and that's in standard form, and that's in general form. So don't forget this equal to 0, and or the other version. All right, let's derive this equation, of course. Okay. So we have a visual here. We have this surface here. That surface is represented in gray. It could be, well, it looks like the sector of a sphere, maybe. I don't know. What else do we have? We have a bunch of stuff going on right here. So we have the surface, and the surface represented by the function big F of x, big F rather. We have a bunch of green lines. Interesting. What are those green lines? So those, or rather curves, those green curves, called Z, C1, C2, C3, if you will. Those happen to be level curves, curves that are intersecting on the edges of on the edge of the surface. What else do we have? We have these vectors in red. Those vectors in red happen to be tangent to the surface at the given point we have chosen here, called P0. What else do we have? Do you see this vector in blue? So this vector is normal to the tangent plane. It's the one that will give us the what's it called? The components or the numbers that multiply x, y, and z. But also, I'd like you guys to see a pretty cool connection from the previous section. Do you see how this vector? Okay, you guys tell me. How is this blue vector, that is the gradient given by the gradient vector, what is its relation to these curves in green? How are those two related? Huh? Yep, doesn't matter. The direction doesn't matter, but how are these related? These green curves with this vector in blue, given by the gradient, by the way. What does that picture tell us? When you see, forget about the vectors in red. Forget about the plane in pink. Forget about the surface. Just focus on the on this normal vector and any of these curves in green. What do you notice about them? What do they form? What is that? They're orthogonal, right? Well, didn't we just discuss that at the end of the previous section? The gradient vectors are always orthogonal to level curves, which at the same time are orthogonal to these tangent vectors, right? That was the second to the last example we did about applications of vectors, right? Of vector. So of gradient vectors and their properties. Okay. So how are we going to describe these trajectories given by Z? This is just going to be some function r of x, y, or x, y, z, depending on, well, actually, let's consider the case version. So these components are going to be functions of t. So let's take the derivative. How about that? Take the derivative r prime of t. That is, let me use dx dt, dy dt, dz dt. That is dotted with the partials. Okay, no, do not dot anything yet. Let's also find the gradient vector, nabla of f, that is the partial of f with respect x, the partial of f with respect y, and the partial of f with respect z. That's how we get the gradient. All right. How about we find the dot product between these two vectors? All right. So let me dot product these two. So x prime. No, let me do dx dt, dy dt, dz dt. All right. Data dotted with f sub x, f sub y, f sub z. Okay, so that means this will be the partial of f with respect x times dx dt plus the partial of f with respect y dy dt plus partial of f with respect z dy dt. All right? Doesn't that look like the chain rule? Remember the chain rule where we had the different branches? So that looks a lot like differentiating ordinarily f with respect t. Okay? And then I'm going to set this equal to 0 just because? No. That's because, do you see this surface represented by the function f of x, y, z equals to 0 represented implicitly, right? So, what is the partial derivative of f with respect t? So take the derivative of 0 with respect t. I mean, what's the derivative of 0? Isn't that still 0? So that's why I can still set this equal to 0. All right? And this looks a lot like the dot product between nabla of f dotted with the derivative of the vector valued function that describes the level curves, and that equals to 0. That's because they're orthogonal. We can see that from the picture. All right? Now, how are we going to get the equation of a plane? Because again, let's go back to the beginning of the semester when we described the equation of a plane. That is, we needed a direction vector. So, did you see how the direction vector for this plane is exactly the same as the gradient vector? So, remember those A, B, and C that were the direction numbers for the vector? This time they're going to be the components of the gradient. That's it. That's all it is. All right. So let's go to the definition. I mean, this first definition is what we just described in the derivation. So remember this. Oops. Ax naught minus ax minus x naught, by minus y naught plus c minus z naught. That's just the equation of the plane. And if the equation is written explicitly, I'm not going to discuss this case. And also the equation of the normal line, it's just the initial point that we're given and t times the component of the vector. So I'm going to show you one example. I think that's going to be perfect timing. All right. So let's see. Find the equation of the tangent plane and the normal line at the point -2, 1, -3 to the ellipsoid given by this equation. Okay, so number one, we need to define an explicit function, or rather an implicit function, x squared over 4 plus y squared plus z squared over 9 minus 3, and set it equal to 0. And because we are defining the big F equals to 0, so if big F equals to 0, then big F is equal to this equation. All right. All right. So we're going to use this equation of a surface to get number one, the gradient. The gradient evaluated at that given point is going to give us the direction vectors. Okay. So nabla of f equals to the partial with respect x. So that'll be 2x over 4, which reduces to 1/2 x, or x over 2, comma, partial with respect y, the derivative of y squared, that's 2y, and partial with respect z, that'll be 2z over 9, which is simply 2/9 z. Okay? Let's evaluate. Let's evaluate the gradient vector at a given point, that is -2, 1, -3. That is 1/2 times -2, 2 times 1, and 2/9 times -3. Let's do some simplifications here. So that's going to give us what? -1, 2, -2/3. Okay, so well, that's something we already did, but now we're going to give these numbers, these quantities, a different use. So now, how do we get the equation of the tangent plane? Number one, so that is the partial of f with respect x times x minus x naught plus the partial of f with respect to y times y minus y naught plus the partial of f with respect z times z minus z naught. Let that be equal to 0. Oh, number one. How are we going to get this x naught, y naught? So number one, x naught, y naught, z naught are these coordinates. While the partial derivatives are going to be the components of the gradient nabla of big F evaluated at the given point where we want to obtain that equation of the plane. Alright, let's go for it. I mean, from here on, it's just going to be substitution, simplify, etc. So that is -1 x minus x naught. What's x naught? Is that a -2? Oh, that makes it a +2, right? Careful. And then +2 times y minus y naught, y minus 1. And lastly, that is plus -2/3, that is -2/3, z minus 3. But that z minus -3 makes it a z plus 3. And let that be equal to 0. And yes, I know what you might be thinking. You don't want to deal with fractions, right? Multiply everything by 3. Or, well, actually, no. Actually, let me distribute the coefficients. So that's -x minus 2 plus 2y minus 2 minus 2/3 z minus 2/3 times 3. That's just going to give us a 2. -2 equal to 0. The rest of the problem is basic algebra. Multiply both sides by 3 to get rid of those rational coefficients. And that's going to give us -3x minus 6, careful to multiply everything, plus 6y minus 6, the 3's cancels, minus 2z minus 6, 0 times 3, that's still equal to 0. Combine like terms, that's going to be -6 and minus 6, that's -2. Oh, minus another 6, that's an 18, right? So that is -3x plus 6y minus 2z minus 18, and that should be equal to, okay, let me continue over here, that equals -3x plus 6y minus 2z, oh, set it equal to 0. I'm going to move the -18 to +18. And this is going to be the equation of the plane for that surface at that given point. All right. But we also want to know the equation of the normal line. Well, if we think of a plane, so like this plane right here, all right? So it's going to have a direction vector, of course. And that direction vector, for sure, is going to contain the same components as that gradient vector. And it's also going to pass through the given point. So that's why we can easily write R of t equals x naught plus at y naught plus bt and z naught plus ct. Again, where do we get those a, b, and c's? A, b, and c are the same components of the gradient vector. And x naught, y naught, z naught, that's simply the point that we are finding the tangent plane and the normal line at. All right? Nothing to calculate, just use the information to write this down. That is R of t equals x naught, that is negative 2, minus t, because the negative 1 times t, and then comma y, which is 1, plus 2t, and z, which is negative 3, plus c, which is, where is the c? Negative 2/3, rather, not plus, it's minus 2/3 t. So that is the equation of the normal line. All right? But of course, I'm going to show you all this in GeoGebra just so you can see what are we calculating. Because again, a lot of crunching number symbols. It's nothing too crazy. It's very formulaic. If you see it, it's very formulaic using everything we have used back in partial derivatives, the gradient. It's just how we put it together to obtain new information. Okay, let me show you GeoGebra. All right. So number one, okay, let me get rid of the plane. So this is the equation of the surface, right, which looks like an ellipsoid. Okay, let me dim the lights a little bit so you can see it better. Anyway. Oh, that's two. Maybe those lights. Anyway, so that's the equation of that's the ellipsoid given by the surface we were given, right? So we want to find the equation of the plane at the point -2, 1, -3, which is going to be this point. Can you see the point? A? All right? We got the equation of the plane in the first part. Do you see how the plane is just touching on one point? It's intersecting the surface at one point. Let me rotate it a little bit. Now, the equation of the normal line should look like if it were stabbing both surfaces and forming, of course, a 90-degree angle with respect to the plane we just find the equation for, and that's given by this curve right here. All right, contains the point, passes through the point. Does that look like it's forming a 90-degree angle with respect to the plane for you guys? That's what we're finding. That's what we're calculating here. All right? I think this is a good place to quit this section. We can finish the next part in the next class.